Oh, we just got it started. What's your quick question, Oksana?
What happens when catalyst is added to the reaction? I know it speeds it up, but does it make it go forward?
So one of the things that we didn't quite finish on that day because we got distracted by lots of questions was what a catalyst does. So catalysts simply speed up reactions without being consumed. Meaning that sometimes we leave them out of the reaction because they're really not a product or a reactant, even though they are critical for making the reaction occur, and they're generally written on the reaction arrow. And so they'll make something happen faster, but they don't change the actual equilibrium, so they have no effect on equilibrium. And so an example might be, if I have A plus B, an equilibrium going to C plus D, if I write on the arrow that I have a catalyst, and we won't even worry about the example of what the catalysts are, we'll talk about what organic catalysts are sort of next semester when we have an entire chapter on them. Yeah, do we have an entire chapter on them? Basically we do. And worry about it then. But here, anytime you see a question with a catalyst, the answer is simply it has no effect on equilibrium. And none of the concentrations change. So our goal for this section is simply to get you the idea of what a catalyst is, to introduce the term. That way when we use it second semester, it rings a bell. Plus, we just honestly kind of ran out of time to talk about things like that. J. Bradley Jr.?
Yeah, what's the second quotation mark? Is this written?
So it's written on the reaction arrow. Meaning it doesn't make sense to write it as a reactant or a product because it doesn't change during the chemical reaction. At least from the end, or from the beginning to the end. No effect on final concentrations, or on the change of the final concentrations. It's kind of out of order, I have to admit.
That's change, right?
Yes.
Start or
Change. So listen to the words. Write the words down. Don't necessarily write what's exactly on the board. But I should work on my penmanship today. Haven't had enough coffee. My hand is still slow and cold.
What color is litmus paper originally? Red, isn't it red?
Well, there's two different types of litmus paper. There's red litmus paper and there's blue litmus paper. I don't know. I would read the book. Seriously, I don't know off the top of my head. I'd have to read the book. Or I'd have to take a piece of red and blue litmus paper and lab and test them.
So you're going to tell us what it does to base?
I mean, we've used it before in lab 5 or 6 times, so I really think that people have the answer for that if they do a little bit of sleuthing on their own. Or I guarantee you if you Google red litmus paper, it'll tell you the answer in under 10 seconds.
What is the last part we know of final concentration?
Okay, so no effect, just like the previous line, on the final concentrations. Meaning it does not change them. Now, how many people, when it came to asking or looking at catalysts, actually read the book, Googled it, did anything else but ask me? Yep, that's Jay's Monday morning sarcasm alert. Okay, so let's pick up in chapter 15 where we left off. We need to review just a bit because if you don't have this down, then what we're going to cover next is a lot harder to figure out what do we know about strong electrolytes? Yeah, they dissociate into ions. %. And then what type of molecules are strong electrolytes?
Ionic.
Yeah, things that are ionic that say aqueous next to them on our charts. And what is the last two categories? Strong acids and strong bases. What is a weak electrolyte? Yeah, meaning most of it is actually written or looks like a molecule. And what things are weak electrolytes? Weak acids and weak bases. So glad Owen comes to class. There's more sarcasm for you. And what about a non-electrolyte? Yeah, it does not dissociate. Meaning it's basically 100%. And what molecules are non-electrolytes? Yep, molecular, and anything that is generally ionic and a solid. So what we're really saying is that depending upon what's in our reaction, it may break apart into ions in water when we actually dissolve it, and some molecules stay together as molecules. And so if we want to get a better understanding of what happens in a chemical reaction, we should represent these molecules in different ways when we write a chemical reaction. So we wrote a ton of chemical reactions in Chapter 8. And the reactions that we wrote in Chapter 8 are all what we call the molecular or unionized equations. Do you guys want me to go back for a second? So what part's unclear?
Is that a 10%?
No, it says 0. Yes, I said ionic compounds that are solids, since they don't dissolve in water, can't break apart to form ions. It would make no sense. How many people did homework 15B? Okay. The first page, that's what all these definitions are, right? So the reason we need these definitions is so that when we write chemical reactions in different ways, we can apply these definitions. So on the test, I can ask you simply what the definitions are, boring, or I can ask you to write chemical equations, probably still boring to you guys, but more exciting to me. So the molecular or unionized equation is the normal equation from Chapter 8. All molecules, or all reactants and products, let's phrase it like that, reactants and products are written as molecules. And an example of that is if I simply say I've got 2 potassium hydroxides that are aqueous plus H2SO4, which is aqueous, and that reacts to form K2SO4, which is aqueous, plus water, which is a liquid. And what technically should I add on that if I was in Chapter 8? Yeah, I really should write plus heat. Now, when we're writing these next two types of equations, and in general, we don't write the word heat. I always make you guys write it because I want you to realize that's why the reaction occurs, and I also want you to write it that way because I want you to just be kind of aware of the fact that this is an acid-base reaction and that they always produce heat. Okay, the next, or the second type of equation that we tend to write is something called the total ionic equation. And what this does is we write molecules that break into ions as ions. And what that really means is that anything that is a strong electrolyte, we write as ions. And so here you have to remember that definition of strong electrolyte so you can apply it. We write molecules and weak electrolytes as molecules. And things that are solids or gases are left alone. So the idea is if something's a solid, it's certainly not breaking apart into ions, and so we leave it together as a solid. If something's a gas, again, it doesn't break apart into ions in solution, and so we'll leave gases alone. So for this reaction, which molecule should be broken apart into ions? Right, so I'm specifically asking which ones are strong electrolytes. So since KOH is a strong electrolyte, really what I should write it as is 2 K plus ions plus 2 OH minus ions. Where did I get the plus and the minus part from? Cheat sheet. That's where we know all the charges for the various ions. What about H2SO4? Strong electrolyte, weak electrolyte, non-electrolyte. Yeah, it's a strong acid, so that makes it a strong electrolyte. So again, we write it as ions in solution. What about K2SO4? Strong electrolyte, weak electrolyte, or non-electrolyte? It's a strong electrolyte because it's ionic, meaning it's a metal and a nonmetal, and it's aqueous. And so it gets written as ions, 2K plus aqueous plus SO4 2 minus aqueous. What about water? Water's what? Well, normal water, if it's very pure, won't conduct electricity. Water that you get out of your faucet might conduct electricity because of all the dissolved metals in it. So water turns out as a non-electrolyte because it's a molecular compound. Or you can also think about it when we defined water as an acid and a base earlier, it's a weak acid or a weak base since it's not one of the strong ones. And so we leave the water alone. And I got to be honest, I shouldn't even be writing heat in there technically, meaning in this section we're worried about how things break apart into ions, not the fact that it forms heat. I just want you to know that it does. So this is saying that if I really had a beaker, because I just said that when we do total ionic equations and things like that, we don't normally write heat in, so we don't really have a rule for what we would do with heat. You can write it in or leave it out for chapter 15, but in chapter 8 you have to include it, right? So I was putting it up there sort of as a reminder about chapter 8. So what this is saying is that in solution what I have floating around is K plus ions and OH minus ions, and I guess I'll just do it like this, and H plus ions and SO4 2 minus ions. And so that's kind of my reactant side. And then if I kind of make a product side, and I'll put my products in red, I really have just H2O floating around, right? And I have K plus ions, and I have SO4 2 minus ions. So that's what the real picture of the reaction looks like, that I've got all these ions floating around, and then I've got additional water molecules that weren't there originally, right? So the next form of the reaction, so this is probably, this shows us everything that's in the beaker in the form that it would be in normally. And then the last reaction, what we want to do is we want to focus down onto what actually occurred. So we call this the net ionic reaction. And in this case, what we do is we exclude any reactants and products that do not change, because that means they did not react. We have a special term for that. Sometimes we call those spectator ions. Just like if you're watching an athletic event, the players play, the spectators just stand by and watch. So the idea is that these ions that aren't taking place in the reaction are kind of just standing there and watching it. It's kind of a non-chemistry term that we apply to some chemistry. So spectator ions. So what that means is that we cross out any reactants and products that don't change. And perhaps we should also point out what we mean by change. So let me define that. Change means there's either a change in charge, a change in state, or a change in chemical composition. So here's where you have to look in your notes, and you'll notice that this should all be on kind of one page. I'm going to go back real quick on my notes in a second here. Is everyone ready or not? Oops. So which ions didn't change? What things are exactly the same on the left side of the equation as on the right side of the equation?
Test.
Yeah, for instance, the H pluses, the H has changed. Because they're H pluses on the left side, they're part of H2O on the right side, right? Yeah, so K pluses are identical, meaning there's two of them, right? They exactly the same charge, and they're exactly the same state, so they didn't change. And what we're really saying is that then in our beaker, what we should do is cross them out. They're uninteresting. They don't take place in the reaction, so they're boring. What else is boring in this reaction? And so what that's saying is the SO4 doesn't take place in this reaction. Now notice the OH and the H plus both change chemical composition, right? Meaning they form water. There's also a change in state from technically aqueous to liquid, but that's a little silly. And so what we're really saying is that our real reaction is 2OH minus plus 2H plus go to form, whoops, did I not balance this reaction? There should have been a 2 in front of the water here and a 2 in front of the water there. So we got to balance the reaction, goes to form 2H2O liquid. And then since all the coefficients are 2, the best answer would be OH minus aqueous plus H plus aqueous goes to form H2O liquid. So that is our net ionic reaction. And what this is really saying is that anytime I have OH minus and H plus, they can react to form water. What it's also saying by omission, which means that you would have to write the previous reaction out, is that K plus SO4 2 minus do not react together. To form a precipitate. Meaning that K plus and SO4 2 minus ions really could care less about each other when they're dissolved in water. They'd much rather be around the water molecules than they would be around each other. And so the idea behind the net ionic reaction is that we get rid of all the extraneous stuff and we focus on things that happen. Meaning, in this case, and I have to admit this reaction is a little boring, but that H plus reacts with OH minus. We'll do a couple more reactions like this so that you guys can get the hang. But also realize it's a process, meaning if I simply give you a reaction and say, write the net ionic equation, you almost have to write the total ionic equation in order to write the net ionic equation, unless you can see the entire reaction out in your head ahead of time, which I got to be honest is possible if you practice this a lot, highly unlikely. So let's take a look at another example. What if I have H2SO4 aqueous plus barium chloride aqueous goes to 2HCl aqueous plus barium sulfate, and that's a solid precipitate. So this is my unionized equation. It's what we normally see in Chapter 8. And you know, it's a perfectly good way to write a reaction. There's absolutely nothing wrong with it. And I would argue that 9 times out of 10, that's the reaction that we want to write. But by writing the total ionic equation, we get a better feel for what's happening. And then by the time we get down to the net ionic equation, we've really focused on what really occurs in this reaction. What's the key components of it? So let's go ahead and write the total ionic. And because I can, I'll write it in green. So H2SO4 is a strong electrolyte, weak electrolyte, or non-electrolyte. Do you have a question, Oksana?
Yeah, what is it saying there?
It says unionized equation.
Is that a plus or
I got a question. How do you just look at it and tell if it's a strong electrolyte?
Well, that's going back to our definitions here. We said that things that are strong electrolytes are going to be things that are ionic, which means that it's a metal and a nonmetal, or it's going to be a strong acid, which you were supposed to memorize which of the 6 or which of the 10 acids were strong, or it's a strong base, in which case you were supposed to remember the 4 that are strong bases. So since this is a strong acid, it means it's a strong electrolyte. And so we can break it apart into ions. Is there another question? Okay, so SO4 2 minus. What about barium chloride? Yeah, it's ionic and it's aqueous. And so we know that it forms barium plus 2 aqueous plus Cl, 2 Cl minus aqueous because it forms the ions, right? And then,
So if it's ionic and aqueous, it means it's strong.
right. What about HCl? It's a strong acid, so it's a strong electrolyte, so it breaks apart into H plus ions plus chlorine ions. And then what about BaSO4? Yeah, and so we leave that.
I have a question. Like hydrogen, like chlorine, why do you put a 2 in front of it?
Okay, so there's a difference between H2, which is a gas, right, versus 2 H plus ions, which are aqueous. So if we had H2 as a gas in the reaction, we'd write it as H2 as a gas. And so what that really is saying is that when I have the hydrogen from the sulfuric acid or the hydrogen from that hydrochloric acid, those really break apart to form the H plus ions.
So like, since it's H2, you just put a 2 in front of it?
Yes, because I mean the reaction still has to balance, right? Meaning that when HCl breaks apart, it breaks apart into hydrogen and chlorine, and because there's 2 HCl's, I have to have 2 chlorines and 2 hydrogens. Same thing with like the sulfuric acid, because when it breaks apart, I get 2 hydrogens that are released and 1 SO4 2 minus that's released.
So the state change of the BaSO4
I'm sorry, I wrote aqueous because I was probably chit-chatting. But it is a solid. Good to see Taylor is paying attention. Good job. So then our net ionic equation. So what things didn't change in this reaction? And so this says that if I have SO4 2 minus aqueous, plus I have some barium plus 2 aqueous floating around, they automatically get together to form BaSO4 solid. And what this says by omission is that basically H plus Cl minus do not react. Meaning if I have a hydrogen ion and a chloride ion in solution, nothing happens. They just are merrily floating along their way. They're more than happy to be dissolved in water. Whereas barium sulfate says, anytime I see a barium and a sulfate in the same reaction, I should figure that they automatically go together to form barium sulfate and precipitate out of the solution. So what it does is it focuses you on what molecules are reactive together and what molecules are not. Okay, one last example.
So today,
Yes.
I don't know if this is a discussion about, but the bottom part, the red part, that's the final answer.
Well, they're all good answers. Meaning if I ask you to write the total ionic equation, then that's the answer, right? And if I ask you to write the net ionic equation, that's the answer. Or if you look at the homework, I ask you to write both of them anyway, and so they're both the right answer.
For the total ionic equation, do we need to show like which ones cancel out or not? Or do we just like remove?
You know, I write it on there as part of the process. I'm not going to mark you off if, as part of your process, you also cross the ones out that aren't supposed to be there. Okay, one last example. If I have magnesium solid plus 2HCl aqueous, they'll react together to form magnesium chloride aqueous plus hydrogen gas. So this is my molecular equation. And I got to be honest, of the three types of equations, in order to do a problem like this, I pretty much have to give you the molecular equation, right? Bless you. Strong electrolyte, weak electrolyte, non-electrolyte.
It's a solid.
Right. If it was an electrolyte, I would have to write it as aqueous, right? So I write magnesium solid. What about HCl? We already said that that's a strong electrolyte because it's a strong acid. So we know we get 2H plus ions plus 2 chlorine minus ions. What about magnesium chloride? Yeah, it's ionic and it's aqueous, therefore it's a strong electrolyte. And I just write it as magnesium plus 2 ions plus 2 chlorine minus ions. What about H2 gas? It's going to be a non-electrolyte because it's a gas. So we just write that as H2 gas. So for my net ionic equation, what things didn't change? Yeah, the Cl's are aqueous on both sides, so we can cross those out. But notice everything else changed, right? Magnesium went from being a solid with no charge to being a +2 and aqueous. And notice that the hydrogen ions in this reaction actually get together and form hydrogen gas. And so they change also. How do I know what?
Magnesium became aqueous.
Well, I mean, here I told you it was a solid, right?
Right.
And here, because it's ionic,
It's aqueous, but when it was apart, is it aqueous?
well, yes, that's the whole idea behind the definition of aqueous. It means when added to water, it does not form a precipitate, so it can't be solid, so that it has to be dissolved in the water. That's the definition of aqueous, right?
The whole compound is aqueous and parts of it are aqueous.
Correct.
Do we know it's aqueous because it reacts with chlorine, right?
I know magnesium chloride is aqueous. Why?
Because it reacts with chlorine. That's how it's
Well, I mean, I know it's aqueous because, I mean, like literally, you know, that was given to you in the equation. Now, if I didn't write aqueous next to it, you'd look on your solubility table, right? So this is telling me what these two things are, right? So my net ionic equation is then magnesium solid plus 2 hydrogen ions. React together to form magnesium plus 2 aqueous plus hydrogen gas. What this is saying is that magnesium reacts with hydrogen ions. It doesn't react with chloride ions. And this says that hydrogen doesn't tend to react with chloride ions when they're in solution. They're happy being by themselves, but hydrogen will react with magnesium. If you do enough of these reactions, what you start building up is a series of what atoms are reactive with each other. You basically build your solubility table. And you can also start to build your activity series from things like this too, from doing series of reactions and looking about what reacts with what under what circumstances. Now, we don't have to do all that work, but we should at least be able to kind of write these reactions. And it's good practice for chapter 8, where you have to start getting your solubility tables out again and looking everything up. You'll have to get your charges out and start looking everything out. You'll have to remember to balance your charges when you're writing things. You have to remember to balance your chemical reactions when you're writing things. All important things for the final on chapter 8 that just happen to also be in chapter 15 nicely. One of those convenient little things.
Is lithium chloride aqueous?
Is lithium chloride aqueous? I'd have to look on the solubility table, but I would argue that yes.
If it's not on solubility table,
Remember, we said if something's not on the solubility table, you should not put the state down on the reaction reaction because you wouldn't know what it is.
but how do we know if the reaction occurs?
Well, there must be something else that's telling you whether a reaction occurs or not. You won't be able to judge it based on the lithium chloride. Do you want to give us the example? So what was the reaction?
Slightly aqueous, we consider it as solid. If we have slightly aqueous, then reaction occurs. Out of it.
Pretty much. So what was your example reaction here?
It was lithium 2CO3 plus hydrogen.
So if I were to write this reaction out on a test, this is what would be given. And then on the test, I'd be responsible for going, okay, I know it's a double displacement reaction, right? And so I know that I should swap the lithium and the chlorine. And I know I should swap the hydrogen and the CO3, pair them up. And then I should go back and check all my charges. And so I know I have to balance that and write H2CO3, right? Now for lithium chloride, I don't know what it is, so don't put anything there. Leave it blank. But this we should recognize as being a common decomposition, meaning we know that it always breaks apart to form H2O liquid plus CO2 gas. So even though we don't know anything about the lithium chloride, because we do know something about the carbonic acid, then we should be able to say that a reaction occurs and complete it. The only thing we can't put down is whether lithium chloride is aqueous or a solid. which is okay because we don't need to know that in order to determine if this reaction occurs or not. We know it'll occur because we form carbonic acid. Oh yeah, I should put a 2 in front of it to finish the reaction. Good eye, Jess. I was focusing more on the carbonic acid part. Okay, let's see. Oh, that was one of the homework questions. What do you know? What? You need to have a 2 here overall if we're doing your homework. Why does there have to be a 4 anywhere? I've got 2 lithiums. I've got 2 lithiums. I've got a CO3. Well, I've got CO2 plus an oxygen from that one. I've got 2 hydrogens and 2 hydrogens and 2 chlorines and 2 chlorines. So it's balanced the way I wrote it. Let's see, what's on the next homework so I don't get too off topic and go out of order, because my notes are, of course, out of order. Okay, so let's do a little bit of review again. One of the things that we said that we can learn from Arrhenius and Brownstein-Lowry and those other definitions of acids is that we can actually write a reaction that looks like this. It looks a little silly, but this really occurs in water, meaning that we really do form, or can consider one water molecule as being an acid, another water molecule as being a base, and so they form basically something that is an acid and a base. And we call this a hydronium ion when it's H3O+. So what we're really saying is that one water molecule accidentally loses its hydrogen to another water molecule. That molecule then can act like an acid, meaning it has excess H+, and that leaves also an OH- ion in solution, which of course can act like a base because it can accept an H+ ion. Or it can also be an electron pair donor. Sometimes you'll see that exact same reaction simply written as water spontaneously breaks apart to form H+ plus OH-. And so whether we write an H+ as H3O+ or we write H+ as just H+, the idea is kind of the same, that there's an extra hydrogen ion floating around. And what we said is that an acid means we have excess H+. A base means that we had extra OH-, and we said it would be neutral if the concentration of OH- equaled the concentration of H+. Now, this only occurs to a very small extent, meaning this is 1 times 10 to the minus 7 molar, and this is about 1 times 10 to the minus 7 molar. When's the last time we had molarities that small and we did anything in class? Meaning, every bottle that you've seen, what's the lowest molarity you've probably seen in class? Usually things are like 1 molar or 0.5 molar, right? Or if you remember the lab that we just did on spectroscopy, I think some of our solutions got down into like 0.05 molar. So nothing is down to 10 to the minus 7. That's 10,000 times, 10,000 times more dilute. And so there's not very much of it around. And so because these are small numbers, we can use a scale called the pH scale to measure the concentrations of acids and bases. So one of the things that I've noticed in life is that human beings don't like numbers that are very far from 1. And that we tend to, especially with very small numbers and negative exponents, have a hard time judging which number is bigger and which number is smaller. And so quite often, whatever we're talking about, we redefine it so that the numbers are between 1 and 100 or something. So like if I want to talk about the size of an atom, I could say, well, gee, that atom is 1 times 10 to the minus 8 or 9 nanometers. Or I could simply say that it's 1 times 10 to the minus like 9 or 10 meters, right? Or I could say that the atom is 10 nanometers wide. And that 1 times 10 to the minus 10, that's hard to picture or hard to relate to something that's, say, 0.8 or 8.7 times 10 to the minus, say, 7. Meaning those numbers are hard. But if I say which one is bigger, 100 nanometers or 200 nanometers, can you tell me which one's bigger? Yeah, and so by changing our scale from talking about things that are really small, so I have to have a huge negative exponent, to things that, are like 100 nanometers or 75 nanometers, I don't know, it seems to fit better into our brain. We have a better picture of what those differences are. So it's the same thing with the pH scale. And what we're really doing is we're saying that the pH can be equal to minus the log of the H plus concentration. Oops. And correspondingly, we can say that the concentration of OH minus is minus the log of the OH minus concentration. So what this does is it takes our scale, instead of going from 1 times 10 to the 0 all the way to 1 times 10 to the minus 14 molar for the hydrogen ion concentration, it makes it go from 0 to 14, where in the middle of our scale we would have had 1 times 10 to the minus 7 molar. Now in our middle of our pH scale I have 7. So what it does is it takes something that spanned 10 to the 0 to 10 to the minus 14 and scales it so that it goes from 0 to 14. Much easier to comprehend, much easier to think about things from 0 to 14. And what that then does is change our definitions a little. We said that an acid has excess H+. Well, that technically means the H+ has got to be greater than 1 times 10 to the minus 7 molar. Or what it also says is if the pH is greater than 7.0. And then neutral is when the concentration of OH minus and the concentration of H plus were the same. And that means that my H plus is about 1 times 10 to the minus 7 molar, so it's equal to that. Or that means that it's equal to exactly a pH of 7. And that anything that's basic means that I had excess OH minus, or what it really means is that the H plus concentration is less than that 1 times 10 to the minus 7 molar, or that it's less than a pH. Oh wait, I got these backwards, sorry. Acids have pHs less than 7.0. Bases have concentrations or pHs that are greater than 7.0. Whoops, I had those flipped. Mostly because I'm not thinking. So this is our definition of a base. This is our definition of an acid. And of course, in the middle we have neutral. So all we're really doing is abstracting the concentration of OH or H+, meaning we're saying, okay, I don't want to talk about things in terms of molarity. Instead, I want to have some other arbitrary set of units like pH. It's the same thing as converting from meters to nanometers, theoretically. Now, mathematically, it's different because it's the log scale, right, instead of a regular scale. So, how many people failed to bring their calculators? Awesome, everyone brought a calculator. Jess? Jess, do you want to run into my office and grab your calculator off of my middle shelf in the middle row, kind of? or I should argue that you're grabbing my calculator. So one of the things here is everyone's calculator is different. And so you're going to have to find different things on your calculator. Can everyone find the log scale on their calculator? So, the easiest way to make sure you're using your calculator right is that we know that if the concentration of H plus is equal to 1 times 10 to the minus 7 molar, then we know the pH better be 7. So when you plug it into your calculator, you'll probably have to type in, minus the log of 1 times 10 to the minus 7 to get that.
Negative mole.
It's the same thing, minus or negative. Meaning on your calculator it might be a little different. So if I type in, for instance, on my calculator, I just type in 1 times 10 to the minus 7, hit my log key, and I get the answer as negative 7. So that means my answer really is plus 7.
Can you say this?
I got positive 7.
Well, it depends on how you type it in. Like, for instance, on my calculator, I can't type the negative sign first. And so I have to, in my head, convert negative 7 to plus 7. If you literally type that into your calculator, for your complicated calculators, that's what you should get. On my calculator, since it's a dumber calculator, it doesn't have as many keys and functions, I have to write it like this. So on a test, what I always recommend is make sure you get what you should expect for the answer, right? So well, which calculator do you have? Okay, you have the same one. So I would have typed in 1 times 10 to the minus 7. And then I would have hit the log key. And then arguably you can hit the minus key on your calculator, or you can convert from minus 7 to plus 7 in your head. So let's do another practice one. What if the concentration of H plus is equal to 2.8 times 10 to the minus 3 molar? What should your pH be? And I don't know the answer. I'll plug it into my calculator too. Actually, I guess if I'm rounding up, 2.6. So on your calculator, Oksana, just type in 2.8 exponent to the 3 negative
No, I understood that.
and push the log
What
key.
was supposed to be on the first one?
Well, you're supposed to get 7.
I got minus 6.
So you typed 1 times 10 to the minus 7.
Oh, yes, yeah, that's what it is. Got out.
Now, are you typing it in as 1 exponent negative 7, or are you typing 1 times 10? Yeah, that's different, right? We've talked about that some calculators you need to use the exponent key, some you'll use that little EE key, which is why we're practicing this. Okay, let's try another example. I don't know, you might be able to type in the minus sign, but I don't think so on these simple calculators.
So we just switched the sign.
Right, so it just takes a little bit of practice. Does that kind of make sense? No, pH has no units, technically. It's a unitless scale, which is strange, but that's the way it is. Because it can't be molarity, because that's not telling me how many moles per liter I have anymore, is it?
So then what is pH?
It's an abstraction, meaning it's simply taking a large scale that goes from 1 times 10 to the 0 to 1 times 10 to the minus 14, which if you think about it, 10 to the 6th is a million, right? 10 to the 9th is a billion. 10 to the 12th is a trillion. So it's taking a scale that goes from 0 to basically several trillion and crunching it down to be between 1 and 14.
So it's pretty much
Yeah, it's literally just scaling things. And the reason for it is because people would much rather say something is pH 5 than to go, well, no, the pH is 1.83 something times, you know, whatever it ends up being. And I don't know since I made it up. A certain part of me says, why bother? But, you know, we always do that in science. We always tend to change scales. Like, for instance, why don't we use the Kelvin scale to measure temperature? That makes perfect sense, because 0 really is 0, right? But people get used to using degrees Celsius. People get used to using degrees Fahrenheit, and so those are the scales we use. It's so much easier to say just change than to actually do it. Why does the United States still use inches and feet when centimeters and meters makes so much more sense, right? So why do we not change? Sheer inertia. Part of it is because I think the U.S. just says, hey, we're the United States. We don't have to do jack shit we don't want to do. You guys deal with our screwed up units. That's my personal theory. Because I don't think it would be that hard to switch slowly. And you'll notice that, heck, nowadays you have to buy an English set of wrenches and a metric set of wrenches. You know, you always have to buy 2 of everything. Okay, if I want to go the backward direction, meaning I know that pH equals minus the log of the H plus, well, if I want to know the H plus concentration given the pH, that's just 10 to the minus pH. And of course, everything we say about the H scale also applies to the OH minus scale that we can have. It's just that we don't normally talk about POH, we just talk about pH. But the concentration of OH minus is equal to 10 to the minus POH. And so, for instance, if I have a pH equal to 7, we know that our H plus concentration better be 1 times 10 to the minus 7 molar. So go ahead and plug that into your calculator and make sure that when you plug it into your calculator that that's actually what you get. For instance, in my calculator I have to type in -7, and then for me that 10 to the x key is the inverse of the log key, so I just do that and I get 1 times 10 to the minus 7 molar. So I always memorize 7, the example, because it's easy and it's a good way to double check if I haven't used my calculator, or I pick up one of your crappy calculators that is too complicated for me and have to use that. So if I was using your calculator, Taylor, which is one of the crappy ones, meaning it's actually better than mine, I would type in probably the 10 to the x key, and then type in -7, and then finish off the parentheses, I think would do it. And I'm guessing. It's been a long time since I've used your calculators.
You have to put that in scientific notation.
You could write it as 0.000001, but I'd write it in scientific notation just because it's easier. Jay Bradley, are you having problems there?
No, I got it.
Okay. You just put your head down on the table. That usually is bad. So I assume that your calculator has a 10 to the x key that you can just use? Okay, that caret thingy is like 10 to the x. So I guess the caret thingy works on your calculators. Is there a 10 to the x key on your calculator even? It usually is just
it's the second for the log.
Yeah, so second function log will give you the same thing. And it might be easier to remember that because it really is the formula we use, and it's the same button. So if I have a pH equal to 5.25, then I should have an H plus concentration equal to, let's see, 5.25. Oops, I gotta remember to type in the damn negative.
Oh, wait, just one.
5.62 times 10 to the minus 6 molar. And I'm writing neutral, acidic, and things like that just as a reminder so that you guys get used to thinking about things as being either neutral, acidic, or basic.
So you do second.
So for you, Brittany, I would type in shift log key.
Yeah, that's the first time I did it. I got huge numbers.
We're confused.
Okay. So let's take a look at your calculator. So for you, it should be second function log. So that's n to the x there. You just type in minus 5.25.
So if you had like, if your pH was like a negative
Should
7,
give you the answer, 5.62 times 10 to the minus 6.
oh, that would be
Don't worry, there's an entire homework that you can get practice doing this on. What a surprise, huh? What a surprise, I tell ya.
Wait, why did we put negatives
Yeah, how do you know?
Negative what?
when we typed it in our calculator?
Because there's a negative in the formula. Because it's H plus is 10 to the minus pH. So see the negative sign right here? So the formula is 10 to the minus pH, meaning it's a little small on the calculator screen or on the screen. So that means that when you type it into your calculator, you've got to type in that negative sign. Because the pH is really 5.25 and the formula says 10 to the negative of that number. Okay, one last thing for this little pH part is that if I write, I have two formulas. If I write, I always know that the concentration of H plus times the concentration of OH minus is 1 times 10 to the minus 14 molar. Or if I'm in my log scale, because of the way the properties of log works, instead of multiplying them, you have to add the pH plus the POH, and that's 14. So log scales have different mathematical properties than our regular scales. So I know that the concentration of H plus times the concentration of OH minus is always 1 times 10 to the minus 14. Therefore, I know when I add them in a log scale, it is also 14. So that means I can ask fun questions like this. Meaning, notice that none of my formulas relate H plus to POH. So what I have to do is do one of two things. I have to take my POH equal to 13, and I can convert that to a pH equals 1, or I can calculate my POH into a concentration of OH minus, which if I plug that into my calculator should be 1 times 10 to the negative 1, but I'll do it anyway just to be careful. Oh, 1 times, wait, 13 negative. And then from pH of 1, I can plug that into my calculator, and I really should get the same answer, so I should just go like this. Where if I have a pH of 1, shift 10 to the minus that, I should get 0.1 molar. Or if I take 1 exponent 13 negative or 1 exponent 14 negative divided by 1 exponent 13 negative is 0.1. So meaning there's two paths. So here I use the formula POH plus pH equals 14. So I basically mathematically solved 14 minus 13 is 1. Here I used the formula that the concentration of OH minus is equal to 10 to the minus POH. And so I got 1 times 10 to the minus 13. Here I use the pH formula that says pH equals minus the log, oops, I'm sorry. I used H plus concentration equals 10 to the minus pH. Here I would have used concentration of H plus times the concentration of OH minus equals 1 times 10 to the minus 14 molar. So what I'm trying to say is there's more than one direction or more than one way to go when doing this. And that if we actually draw it all out, we'll find that we can actually kind of create a little matrix. And I'll show you what that is in a second. But notice I had to use two formulas to do this, right?
So how did you get from the 1 times 10 to the negative 13 to 0.1?
That's the red part here that I just wrote right next to it. Meaning, if I substitute in what I know for OH minus, then if I divide by that value, I just get H plus, right? Oksana?
There were the top red there, H plus, concentration of H plus equals 10 minus pH.
Yes.
So with 10 in minus first degree,
Well, the way you should type it into your calculator would be,
pH is 1, right?
right,
So minus first degree, that's going to be 1, not 0.1.
10 to the minus 1 is 0.1.
10 to the minus 1 is 1.
10 to the 0 is 1. You can mathematically argue this all you want, but that's the rule. 10 to the 1 is the same thing as writing 10. 10 to the 0 is the same thing as writing 1. 10 to the minus 1 is the same thing as writing 0.1. I did, Oksana. It's not going to change. Either you're plugging into your calculator wrong or something else, but that is the answer. I would stake my life on it. Are you willing to stake yours?
You should,
No, it's
but
not
if you
worth
plug the
Exactly.
into this, you have to divide this with this. Alright, so you
So let me show you one last thing and we'll call it quits. And remember, we've got all day tomorrow to work on all of this homework and work the kinks out. We only have one last thing to do in this entire chapter. And frankly, it's something you guys did way back in chapter 9, so we're just going to refresh your brain with it. So we can work out the mathematics, we can practice using your calculators. I just want you guys to get the information so that you have time to work with it instead of getting it just the day before the test or something. So what we're really saying is that I've got a big matrix like this. And there's 4 pieces of information I can know. I can know any one of these 4 pieces of information, and then I have to be able to go back and forth between all 4 of these pieces of information. But notice that there is no arrow going through the diagonals, right? Meaning you have to do, if you want to go from pH to OH minus, you have to do 2 steps. And so if you're going between, say, pH and POH, that's simply the fact that pH plus POH is equal to 14. And if you're going between H plus and OH minus, that's simply the fact that H plus times the concentration of OH minus is 1 times 10 to the minus 14. And then these formulas are if I'm going from OH minus to POH minus, or POH equals minus the log of the OH minus, or that the concentration of OH minus is equal to 10 to the minus POH. And if I'm going to H plus to pH, then that's minus the log the H plus concentration is equal to pH, or that the concentration of H plus is equal to 10 to the minus pH. So you've got 6 equations, none of which you have to memorize. I'll give you them all on the test. What you have to do is be masters of your calculator and masters of a tiny little bit of algebra here and there. And then the other thing you have to know is whether something's acidic, basic, or neutral. Now, you can define, pH greater than 7 is basic, pH equal to 7 is neutral, and pH less than 7 is acidic. I can make a scale for that for POH, I can make a scale for H plus concentrations, and I can make a scale for OH minus concentrations, meaning there's 4 different ways that you can phrase that exact same statement. However, that's a lot of work to memorize all 4 different scales. I think it's much better to just memorize the pH scale and be able to convert any other measurement into pH. Meaning memorize one scale and a few equations instead of a bunch of different scales and a bunch of different equations. But if you want, I can put the other scales up there. It's just, the trouble is after a while you get tired of greater than, less than signs. The equal ones are pretty easy, but the greater than, less than, it's so easy to mess them up because it's a 50-50 thing that you're better off memorizing and mastering one scale and doing math for the rest of this stuff. So, for the rest of the week, what we're looking at is, we're not having labs, so this is just lecture/work day. I'll probably do 15D on this day. And so that means that by Wednesday, homework, what chapter are we on? 15. B and C should be due. And then here on Wednesday, homework 15D should be due, because that's the last day you can even get it looked at. And so what that means is that on Wednesday, we'll review for the exam. Today should be 15A, so Monday should have been... Okay, so I've told you guys this about 5 times, that what day it should be due on. Okay, so let's put it this way. You guys, I told you that it can be due any damn day you want, but remember, if you want it graded before the test, you better turn it in at least 1 day early, right? So, yeah, 15A, we lectured on it on Friday, and I technically said it's due Tuesday. So I'll just say it's due Tuesday, even though there's absolutely no reason, considering the amount of time I spent this weekend and other days, that it would be due. And then technically, since we finished up C today, it can't technically be due tomorrow, so we'll put C due tomorrow, or on Wednesday, right? But if you want it graded before the test, when do you got to turn it in, kind of? Tomorrow, or early enough on Wednesday that I get a chance to grade it, right? And I'll grade everything you guys turn in. It's not very hard. Most of this is really easy to grade because it's just numbers and letters and stuff. Probably only takes me about 10 seconds a page. So we'll have a test on 13 through 16 on Thursday. That gives you guys more time to take the test. And then on Friday, we'll start reviewing for the final. Or that'll be our in-class session to review for the final. Otherwise, I figure we'll probably have several evenings, and I'll just chalk off what, test we're studying for each evening.
When's our final,
So the finals
what times?
is Monday at our normal time. And then I think it was Tuesday. Was it in the afternoon or was it at 10? I can't remember off the top of my head. So it's 1 to 3 on Tuesday. There's a final schedule posted. I've got it in my office if people want to look at it. So what I'm thinking is I'll have office hours tonight from 6 to 8, which means they end at 8 o'clock. So please don't show up at 8 o'clock. And
Is that tonight?
we'll have, that would be Monday night, 6 to 8.
Like tonight, Monday night, you're not talking about finals week?
Right. And we'll have Wednesday from 6 to 8. And then what I'm going to do is I'll do Thursday night. We'll start studying for the final. Maybe we'll do chapters 1 through 3 or 4 or something, you know, and we'll just break it apart into chunks like that. Certainly you can ask questions from any chapter at any time, but I'm thinking that if we break it up into a couple chapters a day, then your guys aren't stressing out too much and you have time to do other things instead of studying chapters 1 through 9 all in one day. Aaron.
So on the final, you have a two-part final. Are you going to say which chapters you're going to have on the first part? So we know
Yes,
which
I
one
have to
is-
look. It's either going to be 1 to 8 or 9, and then 8 or 9 or 10 to 16. And if I remember right, I do 1 to 9 and then 10 to 16.
It makes it a lot easier.
Well, that's why I have a two-part final.
You know I'm not gonna be able to know.
You'll just have to listen to the lecture and, yeah. When you guys have a home game or an away?
That's away. We play at Western Wyoming.
Okay. Yeah, you'll just have to listen to the lecture. I'll post it up online. And I know it's more difficult for you to keep caught up and get caught up, but you got to do your best, Jay Bradley.
So can I get help with chapter 16?
Yes, you can get help with chapter 16 between 1 and 3 also.